All right, we're going to continue through the 0.2 packet for algebra review. On page 10, we're going to look at graphing and analyzing functions. So we're going to sketch a graph of each of the following functions and then state some of the behavior of the function and key features. So the first one, we have 2x plus 1 squared plus 3. So this is a quadratic, and you usually want to reference the parent function when thinking about how we graph. So the parent here would be x squared. So if we think about the parent, and we think about the transformation that occurred, our vertex is now going to be at -1, 1, 2, 3. And then relative to x squared, we have a value of 2. So we're going to scale everything up by a factor of 2. So rather than having a parabola that would go like this, it's going to be a little bit steeper. So we go over 2. Normally that would be 4, but now we're going to go up 1, 2, 3, 4, 5, 6, 7, 8. So we wouldn't even fit on the graph if that's the case, but that's all right. So here we go. We got this parabola, and we're off. Okay, some key features. So our domain is all real numbers. Our range is going to be from the vertex, so 3 inclusive, all the way to infinity. We are increasing after the vertex, so from 3 to infinity, we are increasing, or sorry, not 3, from -1, the x-coordinate of the vertex, to infinity, we are increasing, and we are decreasing from -infinity to -1. Okay, we are decreasing down this way, increasing this way. What else? We want the extrema. So our extrema is we have a different purple. Global min, or an absolute min at the vertex, which in this case is -1, 3. Intercepts, we have no x-intercepts, so our intercept is the y-intercept of 0, and we appear to go through 0, 5. End behavior, we have as x goes to infinity, f of x is off to infinity. As x goes to -infinity, f of x is also off to positive infinity. So it's symmetric, we're both off to infinity either way we go. All right, our second function is linear, so it has the parent function y equals x. Let's mix the colors up. Go red. Okay, now that's in point slope form. If you wanted, you could convert that to y equals mx plus b if it helps. But point slope form, it's the general form is y minus y1 equals mx minus x1, where x1, y1 is some point on the line. M is the slope. So if that's the case, that means x1 would be -3, 1, 2, 3, and y1 would be +4, 1, 2, 3, 4. So that's my x1, y1. And then I can use the slope of -1/2, so I go down 1 over 2, down 1 over 2, 1 over 2. And I'm going to connect that and see if we can create a nice straight line here. Okay, domain of linear functions is all real numbers, as is the range is all real numbers. We are always decreasing on the interval -infinity to positive infinity. The function never changes direction. We have no extrema, there's no max or min values. Intercepts, we have a y-intercept at 0, 3, and an x-intercept at, it appears, 1, 2, 3, 4, 5, 0. Okay, and you could check either of those by plugging in 5 for x, and we should get 0 for y. So yeah, that's great. And then end behavior on the ends, as x is off to positive infinity, f of x is going to -infinity, and as x goes to -infinity, f of x is going to positive infinity. So we have the opposite behavior. One way we're going down, other way we're going up. All right, now we have our square root function. So if we think about the parent square root function, we would just have y equals square root x. Look a little something like this, right? So we have to think about how is that transformed based on our function. So x plus 4, that gives our new coordinate of the vertex at -4. That's the last thing we can plug in because square root of 0. And then at -1 because we're shifting down 1. So we have the coordinate -4, -1 as our vertex, or our sort of end there. And the a value is 2, so rather than going over 1 up 1, we go over 1 up 2. Rather than going over 4 up 2, we go over 4 up 1, 2, 3, 4. And then we have one more. We could go over 9 and up 3, but we'll go over 9 up 6. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. Okay. So I'm just using the natural square roots, like square root of 9 is 3, square root of 1 is 1, square root of 4 is 2. So that tells me how far to go in the x, and then I go to the y. Maybe we look something like that. Okay, the domain of this function, so we're going from -4 to infinity. The range, we are going from -1 to infinity. Whoops, I should have inclusive on both of those. So -4 inclusive and -1 inclusive. The function is always increasing, but it is doing so on the interval -4, infinity. Extrema, we have min, an absolute min at -4, -1. Intercepts. So intercepts, we can see we have 0, 3 is our y-intercept. Our x-intercept is less clear. We might actually want to solve that. So we get 0 equals 2 square root x plus 4. Whoops. -1. So 1/2 is equal to the square root of x plus 4. Squaring both sides, you get 1/4 equals x plus 4. So x is going to equal, so 1/4 minus 4, that's 16/4, -15 over 4. So that'll give us -15 over 4, 0. And let's see, end behavior, put over here on the end behavior, as x is off to infinity, f of x is off to infinity. But then on the other end, x is heading towards -4, and f of x is heading to -1. Okay, and we'll just sort of scribble this work here. Cool. All right, number 4, we have a cubic function. So this is a polynomial. We have some key features. So we can start with graphing our x-intercepts. So I have a 0, +1, and 1, 2, 3, -3. Honestly, I don't want my graph to be so squished. So I am going to go 0. I'm going to scale, make 2 boxes equal to 1, and then 1, 2, 3, 4, 5, 6 boxes will be -3. So I'm going to make this scale such that this is 1. Okay, so that's good. This is a positive x cubed is the parent function here, so we know our end behavior is going to look a little something like that. Short of calculus, we probably aren't going to be able to 100% tell where the maximums or minimums are. So let's head over to a graphing calculator, and that's going to be how we're going to have to figure out that information. Okay, frustratingly, my TI-84 on the computer is not working well, so I'm just going to use Desmos, and using Desmos, we find that these coordinates are at like -1.89-ish, so comma 6.065. So this whole function is not doing exactly what I would like it to do. We're going to make our y scale 1 unit. So if we go over 1 unit in the x, negative 1.89, and then up 1, 2, 3, 4, 5, 6-ish, 6065, we're somewhere right around here. Okay, so I'm going to say negative 1.87. This is an estimate, and then we'll call it 07. And then our minimum down here is 0.535 and almost negative 1, so somewhere down here. 0.54 and negative 0.88. Okay, and so now I can fill in, and we'll just sketch the rest of our graph. Great. So it looks a little something like that. The curve is not as smooth as I'd like it to be, but that's all right. Domain, so all real numbers for cubics. Range, all real numbers. What else do we need here? It is increasing from 0 to negative 1.87. And then again from 0.54 to infinity. I don't know why I said 0. I mean infinity, negative infinity to negative 1.87. So that's what I should have said for increasing, because it is increasing this way and this way. And then we are decreasing from there to the coordinate. So we are decreasing from negative 1.87 to 0.54. Remembering that the intervals we're describing are basically always based on x. Our extrema, so we have a local or relative max at that coordinate negative 1.87, comma 6.07. We have a local min at the coordinate 0.54, comma negative 0.88, or at least approximately so. Intercepts, so we have intercepts, x and y intercept of 0, 0. We have an x-intercept of negative 3, 0, and an x-intercept of positive 1, comma 0. Finally, our end behavior here, as x goes to infinity, f of x is also off to infinity, and as x goes to negative infinity, f of x is also off to negative infinity. So for it to be a cubic or an odd polynomial, the ends will go off in different directions. Okay. Scooting on along here, we have f of x equals e to the x. So this is an exponential function. Generally, these functions have asymptotes. And by generally, I mean kind of always. And they have horizontal asymptotes. And yeah, so I'm going to make my scale here just 1. E, recall, is approximately 2.7-ish. So if I go up 1, 2, and then a little more, that'll be like an e. E squared, let's check that out. E squared is approximately 7.4-ish, so I'll count, e to the first is about 2.7, e to the 0 is 1, we always have this 0, 1 for exponential parents, and then e squared is about 7.4, so we go 1, 2, 3, 4, 5, 6, 7.4. So we're shooting off exponentially, and then we are also approaching our asymptote. Okay, domain is all real numbers. Our range is from 0 to infinity. What else? We need to talk about the increasing and decreasing intervals. So we're increasing on our whole domain, negative infinity to infinity. We are never decreasing. We have no real extreme values. We don't have any maxes or mins. We approach 0 and we go off to infinity, but that's about it. Our intercepts, we just have a y-intercept at 0, 1, because anything to the 0 equals 1. E to the 0 is also 1. End behavior, as x goes to positive infinity, our outputs, f of x, is also getting bigger and bigger and bigger, off to infinity. And then as x gets more and more negative, our outputs get closer and closer and closer to 0. They'll never actually reach it. Okay. Next one, we have a logarithm. So log x, recall, is log base 10 of x. Logarithms are the inverse function of exponential functions. They have vertical asymptotes as opposed to horizontal. Y equals 0 is the default with no switches or shifts. 10 to the x would be the exponential inverse here. So if we know 10 to the 0 would give us 1, that means log base 10 of 1 equals 0, giving us the coordinate 1, 0. So logs by default will usually go through this coordinate 1, 0, just like 0, 1 is on the exponential functions. Then the next sort of point that we would see is log base 10 of 10 is 1. So an input of 10, 2, 3, 4, 5, 6, 7, 8, 9, 10 gives us an output of 1. Then we want to connect this log here. And we also come off, as we put in fractions, we will get more and more and more negative outputs. Okay, so the domain of this function is from 0, not inclusive, off to infinity. Notice that that's comparable to the range of some exponential function. But the range is all real numbers, which compares to the domain of the exponential, because they're inverses. We are still increasing on our entire domain. As we go from left to right, we are always increasing. We're going up, going up. The rate of increase is a little different, but we're still always increasing. So from negative infinity to positive infinity. Intercepts. So we won't have a y-intercept because we've got an asymptote at the line y equals 0. But we do have that x-intercept at 1, 0. And then our end behavior, as x goes to infinity, we can continue getting bigger and bigger and bigger outputs. So that's also off to infinity. As x goes to 0, that's sort of our other end of this function, f of x is going to negative infinity. So as we put in closer and closer numbers to 0, we get more and more negative numbers. Okay, number 7, we are also going to have a logarithmic function. So it's going to follow this sort of theme, but we have an x minus 4 inside the function. So now, when I plug in 4, I end up with 0. So if I plugged in 4, I would get log base 2 of 0, which is undefined. Meaning that my asymptote is now at positive 4. So I'm going to go 1, 2, 3, 4, and there's my asymptote. Now there's nothing else really going on with this function, so it's going to follow the rest of the general characteristics of a log. Instead of that 1, 0 coordinate, we're actually going to get 5, 0 as our new coordinate, because log base 2 of 5 minus 4 becomes log base 2 of 1, which is 0. Since it's log base 2, the next time I'll get a nice power of 2 is just one step to the right. Log base 2 of 6 minus 4 will get me to 1. So I'll get this coordinate right here, 6, 1. And then the next time I'll get a nice integer power of 2 would be if I plug in 8. And so 8 will give me 2. So I'll go 6, 7, 8, 1, 2. That's all the integers that'll fit on my graph. And then, of course, I have the fractional results inside the function, which send me off in the negative direction. So my domain, in this case, my asymptote is at 4, but we are headed to infinity on the rest of it. My range is all real numbers. I can get out any output I want. My interval increasing is on its entire domain, but in this case, that is from 4 to infinity. My intercept, I have no y-intercept, I don't cross that axis, but I do cross the x-axis at the coordinate 5, 0. And then on the end behavior, I am going as x goes to infinity, f of x is off to infinity, and then the other side of this function is x approaches positive 4, f of x is headed to negative infinity. And there are no real max or minimum values here because we're either going to positive or negative infinity in either direction. And our last function, we have a quadratic. So the parent function is x squared. We'll have some sort of parabola, and it's going to be facing up. However, we probably want to factor this. Hopefully that'll give us, it'll definitely give us the x-intercepts. Maybe that'll help us get the vertex, and that should be enough information. So if I want to factor, I find the AC, which is -8, and B is -7. So that would be like, multiplies to -8, adds to -7. Concerningly, I'm not sure I can come up with anything. It looks like it should work. Oh, okay, -8 times +1. Haha. Okay, so we can factor this by splitting the middle term. So we could say 2x squared plus 1 minus 8x, plus 1x, sorry, minus 8x minus 4. We end up with 2x, x plus 1, and then minus 4 times, sorry, I'm not in the zone right now. Let's try that again. We end up with x, 2x plus 1, minus 4 times 2x plus 1, giving us the factored form of 2x plus 1 and x minus 4. Okay, that would give me zeros of -1/2 and +4. I'm going to choose a scale here so that one box is actually a half. Okay, and two boxes would be 1. So I'm choosing the scale on my x just so I can put -1/2 right here. And then 4 would be 1, 2, 3, 4, 5, 6, 7, 8 boxes out here. And then if I wanted the x-coordinate of my vertex, if I find the middle between -1/2 and +4, well, that's the same as 8 over 2, which is equal to 7 over 2, which equals 3.5. Using my scale, though, that is going to be at... well, it should logically be at... why is this so confusing? 1, 2, 3, 4, 5, 6, 7. But that doesn't really make sense, huh? What did we do wrong here? Oh, because... no. Very suspicious. Actually, that doesn't even look right. Why would 3.5 be halfway between 1/2 and 4? Oh, because we need to average that. It's the midpoint of the two of them. Oops. So we add them together, average it, so it actually ends up being at 7 over 4, which is approximately equal to exactly equal to 1.75. So using my scale of a half, we go 1.5, and then another half of that. So that's where my vertex is going to be. Where do we reckon the y-coordinate of the vertex will be? Well, we'd have to plug that back in to our quadratic, which I suppose nothing to it but to do it. So we can do 2 times what we say, that's 7/4 squared minus 7 times 7/4 minus 4. So 7/4 squared, that's 2 times 49 over 16. Sounds like 98 over 16 minus 49 over 4, which presumably is 98 over 8. Minus 4, which is 64 over 16. Convert that 98 over 8 into 16ths. 196 over 16. Combine all that together, we would have -260, and then 162. So we get -162 over 16. Which would be 10 and 2/16, or 10 and 1/8. So our y-coordinate of the vertex is negative 10 and an eighth. Okay, so I'm going to choose to scale my y values by 1. So we'll pick my little scale here. Then I'll go down to negative 10 and then just a tiny bit more. And that's my vertex. And then off we go. My y-intercept is going to be 1, 2, 3, 4. So I'll try to include that. Very imperfect graph. Kind of pointier than I'd like it to be. But what can you do? Nothing's perfect, especially on this tiny little grid and an iPad. Great. Okay, so the domain is all real numbers. Range is going to be from that vertex, negative 10 and an eighth to infinity. What else are we supposed to have here? We are increasing from the x-coordinate of the vertex. So we're increasing from, that was 7/4 to infinity. We are going to be decreasing from negative infinity to 7/4, right? Because we're decreasing all this way, decreasing, increasing. That relative, or actually it's an absolute max, minimum, sorry, is 7/4, comma, negative 10 and 1/8. And usually I don't like mixed numbers, but honestly, there's not enough space for me to do all this out, so I'm just rolling with it. Intercepts, ints. We have at 0, comma, negative 4 is our y-intercept. What a mess. High quality video. We have, what do we say, 4, comma, 0, and we said negative 1/2, comma, 0. And then our end behavior, okay, as x goes to infinity, f of x is off to infinity. As x goes to negative infinity, f of x is also off to positive infinity. So it's symmetrical, right? We have to go in the same direction with an even function. All right, so that one was kind of tricky, but we rocked it. Very good. Peeking on ahead. Oh, more graphs. Delightful. All right. Rational graphs. Let's see here. We're going to factor these. I'm just going to go ahead and factor them because, yeah. So we're going to get x plus 4, x minus 1 over x plus 3, x minus 1. We have this common factor of x minus 1. So we're essentially x plus 4, x plus 3. It's a rational function. We're going to have a horizontal asymptote at y equals 1. It's because we have the degree of the numerator and denominator is the same. And so as we plug in bigger and bigger values, we're approaching this line y equals 1. So we'll put that down. And then in our denominator, we have x plus 3 giving us x of negative 3 is our vertical asymptote. Then I probably need to plot some other points. If I plug in 0, I'm going to get out 4/3, which is right about here. Kind of annoying. If I plug in, well, no. It's not going to be any nice integer coordinates. If I plug in negative 2, I would get 2 over, oh no, that works, 2 over 1. So negative 2 gives me 2. Which seems a little weird, but okay. And then there we go, we'll draw our little rational. Cool, and then that's going to be symmetric, so over here we would expect a point and some other points, but whatever, off we go. I guess we could know that x-intercept would be negative 4, 0 anyways. All right, so our domain is all real numbers except x cannot equal. Oh, I almost missed something. We have a hole at positive 1. So right here, we got a big old hole in the function. So ignore that I drew a line through there. There's a hole. So x cannot equal 1, and x cannot equal negative 3. Our range is all real numbers except y cannot equal 1. Increasing and decreasing. Now, this is really weird. This function is decreasing on its entire domain. If we look at it on the left part, like technically we're decreasing, decreasing, decreasing on this whole piece of the function. And then if we look over here, we're always decreasing. So moving left to right, we're always decreasing. So over our entire domain, we are decreasing. If we specify the interval, we would go from negative infinity to negative 3. And then we would be decreasing from negative 3 to positive 1, and then from 1 to infinity, because we have to sort of piece together the holes in our function, or the asymptotes. The intercepts of our function, we said there is an intercept at negative 4 comma 0. There's an intercept at, the y-intercept we said was at 0 comma 4/3. And that'll do it for us there. Then our end behavior, there's no relative max or mins here. End behavior is x is off to infinity. F of x is heading towards that horizontal asymptote of 1. As x goes to negative infinity, f of x is heading toward that horizontal asymptote as 1. It's an end behavior asymptote. Okay, so there goes our rational function. Yahoo! Moving on, guess what? We get another rational, so let's factor that thing. So we're going to get 2 times, x squared minus 1, which will factor in the bottom. We'll have x plus 2, difference of squares, x minus 2, and then this will factor in the numerator to 2. Another difference of squares, x plus 1, x minus 1, over x plus 2, x minus 2. Okay, great little practice factoring. Nothing cancels, no common factors in numerator and denominator. Because those denominator factors don't have anything to cancel with, they're just asymptotes. So I'm asymptote at positive 2 and at negative 2. Okay, degree of the numerator and denominator is the same, meaning that our horizontal asymptote, again, will be based on the coefficients, but this time it's 2 over 1, the lead coefficients. So we're going to have a horizontal asymptote at y equals 2. What a delightful function. Numerator will tell us the x-intercepts. So we'll have x-intercepts of negative 1 and positive 1. So here's 1, here's the other. Yeah, if we plug in 0 for x, our y-intercept is going to be at positive 1/2. So we have to end up here. Now, all of this is only going to be possible if the function looks a certain way. So you could plot a bunch more points if you want. But all of this is only really going to be possible if, in fact, we go something like this. So we approach that asymptote, cross the y-axis or x-axis once, and probably approach the asymptote there. Then we have to cross this intercept only once. We never can come back, so we're going to have to shoot over the horizontal asymptote, which is okay. It's an end behavior asymptote, not a just pure asymptote. And then to not cross the x-axis on the other side, we probably are going to look something like this. Okay? That's as far as I care to graph. To check to see that we cross this horizontal asymptote, I can set the equation 2 equals 2x squared minus 2 over x squared minus 4. So I'm setting it equal to the horizontal asymptote at y equal 2. And then I can just solve this. So I get 2x squared minus 8 equals 2x squared minus 2. That's actually not a great sign. Because these would cancel, implying negative 8 equals negative 2, which would imply we don't cross the horizontal asymptote. All right, let me graph this on Desmos super quick, and I'll get back to you. 2x squared minus 2 all over x squared minus 4. Oh, wonderful. Okay, we're just going to cut that. Okay, so cut all that, that's fine. Okay, based on our factored form, the common factors, there are none, so in our denominator we have x plus 2, x minus 2, giving us asymptotes at -2 and +2. From our numerator, we have x-intercepts at 0, -1, or sorry, -1, 0, 1, 0. Y-intercept, if we plug in 0, we would get 1/2, so it's something like this. Our horizontal asymptote would be something like this. Okay. Because the degree of the numerator and denominator is the same, we have a 1 here, coefficients, so on. Okay, based on this, I can sort of get the shape of my graph because I've got to be contained in these asymptotes. And then I don't really ever cross the x-axis again, so I'd probably look something like this. And you could test more points or you could try to find it out, but we can say pretty confidently that this is the case. Okay, so our domain is going to be all real numbers, but not our asymptote, so x cannot equal -2, and x cannot equal +2. Range is all real numbers, but we don't cross this horizontal asymptote in this case. You could plug it in and check, but just based on the shape of the graph, like we're pretty confident about that. So we're going to say y does not equal 2. Okay, we are increasing, so the function's going up here and then up here. So we would say we are increasing from -infinity to -2, and then from -2 to the x-coordinate there, that seems to be a max, 0. We are decreasing then from 0 to +2, and then 2 to infinity. What else do we have? We do have that relative max, at that y-intercept of 0, 1/2. I mean, I cheated a little bit and looked on Desmos, so I know that to be the case. Maybe you wouldn't be able to figure that out otherwise. What else do we need? Intercepts. Put them up here. We have -2, 0, 2, 0, and 0, 1/2. And then our end behavior. So on our ends, we'll put this up here, as x is off to infinity, f of x is headed towards our horizontal asymptote of 2, and then as x goes to -infinity on the other end, well, the function's also going to that horizontal asymptote of 2. Okay, cruising along here. Let's get rid of this. Too much. Good job. Okay, 2 more. Piecewise function here. F of x equals -x². Call it green on this domain. So we're split into a couple domains. We're going to put this all together. I'm going to start with this constant piece. So the function's equal to 3 from -2 to +7. So -2 inclusive, we are equal to 3. And then we scoot on all the way, 1, 2, 3, 5, 6, 7. We've got an open circle. Beautiful, that's easy. -x² when x is less than -2. So -x² would go like this. Boom, 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 boom. But we don't have that for the full domain. So we're going to put it starting right here with an open circle. And off we go. Great. Then we had x minus 5 squared plus 2 when x is greater than or equal to 7. Well, x minus 5 squared plus 2 has a vertex at 5, 2. So we'll go 1, 2, 3, 4, 5, 1, 2. That's where it ought to be. Then it is just our regular function, so we'll go here, and then 1, 2, 1, 2, 3, 4, compared to the parent, then 3, and then 9. But yeah, that's kind of what we're doing. So that would shoot off like this, and then we're not actually here on our domain. So this looks a little weird. Yeah. Okay. Interestingly, our domain is all real numbers because even though we have sort of jumps in our function, we are defined, we can plug in any value for x and get out some output. Our range is not all real numbers because we have these jumps. So our range goes from negative infinity to, what is that coordinate? -4, not inclusive. And then it goes to 3. It kind of hangs out at 3 for a bit. And then it also goes from +6 to infinity. Okay, so 3-piece range. Intercepts. We only have a y-intercept, and it is at 0, 3 from our constant function. We don't have any relative max or mins. I'm not going to put those vertex coordinates. I mean, maybe someone could argue that they are, but I'm just not interested. What else? Increasing, decreasing, and end behavior. All right, we are increasing. You'll notice if we look at our function, we're increasing here, we're increasing here. Okay, inc. When we're constant, we are not increasing. That's constant. So we would say we are increasing on the interval -infinity all the way to when x is -2, not inclusive. Then we start increasing again, inclusively on x is equal to 7 to infinity. And then we close that off. Then we are decreasing never, and then our end behavior. Okay, on our ends, as x is off to infinity, f of x heads to infinity. As x goes to -infinity, guess what? So does f of x. So that's pretty nice. Great, so that sums up that piecewise function. On to the last one, yahoo! So we have an exponential. There's no vertical shift. There is a vertical stretch, but our asymptote is still here at y = 0. Good. Plug in 0, we get 1. No, we don't. Plug in 0, we get 3, because 2 to the 0 is 1 times 3 is 3. Plug in 1, 2 to the 1 is 1, we get 6. 1, 2, 3, 4, 5, 6. And that's probably all that's going to fit there. Yeah, would we ever get any other integers? No, probably not. So we're going to sketch this graph here. And there we go. Okay, our domain, all real numbers. Our range from 0 to infinity. We don't really have any max or mins. Our only intercepts to speak about are the y-intercept, or is the y-intercept at 0, 3. We are always increasing over domain, so we're increasing from -infinity to +infinity. No extrema. Yes, our end behavior, as x is off to infinity, f of x is also off to infinity. Guess we're not allowed to write there. And as x goes to -infinity, f of x is off to the asymptote of 0, but never gets there. Okay, so I hope that went okay. Kind of exhausting to do all these graphs, to be honest, but it's great practice. Hopefully me doing this was helpful. Yeah, so thanks for checking it out.